My name is Anthony Travado, ZID 5584908, and in this video I'll be explaining my results to the Understanding the Solar System experiment. Before we get into the experiment, let's go over Kepler's laws which describe planetary motion. Kepler's first law, also known as the law of ellipses, states that planets orbit their star in elliptical pathways, with the star located at one focus point. This simply means that planets orbit in ellipses rather than perfect circles. Kepler's second law, also known as the law of equal areas, states that a line joining a planet and its star will always sweep out equal areas in equal time. In this diagram, according to Kepler's second law, the planet will sweep the area of A1 in the same time that it will sweep the area of A2, meaning it must travel at a faster velocity around A1 compared to A2 in order to sweep the area in the same time. As a result, planets travel faster across their perihelion compared to their aphelion. Kepler's third law, also known as the law of harmonies, states that the square of the planet's orbital period is proportional to the cube of the semi-major axis of the planet's orbit. This means that the further a planet orbits from its star, the longer it will take to complete one revolution around its star. So let's get into the experiment. We will begin by looking at a planet and moon simulation and examining their motion. In this simulation, the planet represents the Earth at 1 Earth mass, and the moon represents the Earth's moon at 1 moon mass. What we see when we run this simulation is that as the moon orbits the Earth also moves as if it is orbiting around a common center of gravity. Earlier, I ran planet and star simulations where I altered the masses of the planet and the star in relation to the mass of the Earth and the mass of the Sun respectively, and examined the behavior of their motion. Despite me altering the masses of the star and the planet, the mass of the star always stayed significantly greater than the mass of the planet. This meant that the center of gravity was only slightly off from the center of the star. So while the star and the planet do technically orbit a common center of gravity, it's so close to the star's center that it's hardly noticeable. However, in the planet and moon simulation, the mass of the planet was not significantly greater than the mass of the moon in comparison to the planet and star simulation. This meant that the center of gravity was further from the planet's center compared to the planet and star simulation, so its movement was more noticeable as the planet orbited around that common center of gravity. Now we're switching to a planet and star simulation and examining how a planet's distance from its star affects its orbital velocity and orbital period. In this experiment, the planet will represent the Earth at 1 Earth mass, and the star will represent the Sun at 1 solar mass. I've selected 4 distances for the planet, measured in astronomical units, those being 0.5 AU, 1.5 AU, 2 AU, and 2.5 AU, which I will use to compare the effect of orbital distance on orbital velocity and orbital period. Lastly, each unit in the following grids will represent 0.5 astronomical units. Here's a summary of the data gathered. From these results, we can conclude that as we increase the Earth's orbital distance from the Sun, we increase the Earth's orbital period, which aligns with Kepler's third law. We also saw that the closer the Earth was to the Sun, the faster its orbital velocity had to be to remain in a close to circular orbital pathway. This can be explained using Newton's law of universal gravitation. From this law, we can see that if we decrease the orbital radius of the planet, we increase the force of gravity exerted on the planet by the star. In order for the planet to not spiral into the star as the orbital radius decreases, the planet must travel at a faster velocity so that it is falling towards the star at the same rate that its orbital pathway curves around it. If we apply this to our own solar system, we can determine that Mercury, the closest planet to the Sun, will have the fastest orbital velocity due to having the shortest orbital radius, whereas Neptune, the furthest planet from the Sun, will have the slowest orbital velocity due to having the largest orbital radius. So what have I learned from this experiment? I've learned that orbital velocities play a crucial role in maintaining close to circular orbital pathways, how changing the mass of a planet or a star can impact on the shape of the planet's orbital pathway, and why a planet appears to move more in comparison to a star when they have celestial bodies orbiting it. Thank you.